All right, let's talk about one of the biggest engineering puzzles out there. How do you keep nuclear waste safe? And I don't mean for a few years, I mean for thousands and thousands of years. It's a problem that, as you'll see, requires some seriously clever thinking.
And that brings us right to the heart of the problem for the scientists designing these waste sites. You need to be 100% sure that these containers will stay sealed for millennia. But you can't just dig them up in a few hundred years and, pop the lid to see how things are going.
So the plan is to seal the waste inside these massive steel and concrete containers. Think of them as the ultimate lockbox, and then bury them deep underground. But to guarantee that's actually safe, we have to know exactly what the chemical environment is like deep down inside that box.
But of course, there's a catch. The conditions in there are just brutal. We're talking extremely alkaline, basically like drain cleaner, with crazy high hydrogen pressure and zero oxygen. Trying to stick any kind of normal sensor in there to get a reading? Forget about it. It would get destroyed or just give you totally bogus information.
So, how in the world do you measure something you can't actually measure? Well, this is where things get really cool. It's kind of like a spy movie, but for chemistry. If you can't go in yourself, you send in a team of undercover agents.
First, though, we need to understand the one key thing the scientists are really after. It's called the redox potential, or just EH for short. Now, don't let the name trip you up. The easiest way to think about it is like the chemical mood inside that lockbox. Is it a generous, giving mood where it's handing out electrons? Or is it an aggressive, thieving mood, trying to snatch them away? And inside our concrete lockbox, there's one thing, and one thing only, that sets that mood. It's the slow, steady corrosion of the steel bars inside, all happening without any oxygen. This one process is so powerful, so dominant, that it basically becomes the chemical boss. It runs the whole show. So, the entire safety plan for this whole project hinges on figuring out the exact mood this boss is creating. Is it a calm, stable environment that's going to keep all that waste safely locked down? Or is it something more volatile? They absolutely had to find out.
And since you can't just walk in and ask the boss what it's up to, they did the next best thing. They sent in those chemical spies we mentioned to do a little bit of reconnaissance.
So, let's meet the team. We've got uranium, selenium, antimony, and molybdenum. And these aren't just any old elements pulled off the periodic table. Nope. These are special agents known as redox-sensitive radionuclides, which means they are perfectly suited for this kind of spy work. Think of these guys as chemical chameleons. Their whole purpose is to change their very structure, their chemical state, based on the redox mood of whatever environment they're in. It's like they record a message about what they've seen simply by changing their form. So, here's the mission plan, step by step. First, you drop the spies into a liquid that's a perfect simulation of the water inside the concrete. Next, you introduce the target, the chemical boss, that corroding steel. Then, you just let it sit. You let the boss's environment work its magic on the spies. And finally, you pull the spies out for their debriefing, to read their report. All right, mission accomplished, the spies are back. We know they've been changed by their experience inside, but how do you get them to talk? How do you actually decode a report that's written in chemistry? Well, for that, you need a really special interrogation tool. And that tool is an incredibly powerful X-ray technique called XANES. Honestly, the best way to picture it is like a super high-tech fingerprint scanner for atoms. It can look at one of our spies and generate a unique chemical fingerprint that tells us its exact state, revealing precisely how it was changed. And wow, the results were just fascinating. The X-ray scan was basically a chemical lie detector, and the spy's stories were crystal clear. Each of these charts is one of those fingerprints, and you can see it plain as day. Spies like uranium, selenium, and antimony came back completely transformed. The chemical boss had definitely been at work. Now, here's the really crucial point. They weren't just changed in some random way. They were specifically reduced. And in chemistry, reduced is just a fancy way of saying they gained electrons. That generous move we talked about? Well, the chemical boss was basically forcing these extra electrons onto our spies. So each of these transformations is a critical clue. Using those clues, scientists could then pull out a kind of chemical decoder ring to translate each spy's report into a hard number. They calculated the exact etch value, the precise mood that had to exist in there to cause that specific change. And this is where it gets really amazing. It didn't matter which spy they interrogated, uranium, selenium, antimony, they all came back telling the exact same story. All of their reports pointed to the very same signature number, about negative 456 millivolts. All the evidence was pointing to the same conclusion.
And that number, negative 456 millivolts, it isn't random. It is the known fingerprint for a very specific chemical reaction happening on the surface of that corroding steel. So get this, the spies didn't just report on the mood, they essentially unmasked the chemical boss and revealed its true identity.
Okay, so this is the big payoff. We have the number. We've identified the boss. But so what? What does that actually mean for the safety of our nuclear waste lockbox? Why does this one specific number matter so much?
Well, it matters a whole lot, because that very specific mood, that negative 456 millivolts, creates what's called a highly reducing environment. And this environment forces any dangerous radioactive elements that might get loose to grab onto those extra electrons, and when they do that, they transform. They go from being something soluble that can travel in water to becoming stable, solid particles that literally cannot move. They're locked in place.
So in short, our chemical spies proved that the chemical boss, the very steel corrosion we might have thought of as a problem, is actually the hero of this story. It's the ultimate security guard. It creates the perfect chemical prison, turning mobile threats into harmless, solid prisoners, locked down for the long haul.
This incredible piece of detective work, it doesn't just give us confidence about nuclear waste storage. It gives us a brand new tool. It proves we can use these chemical spies to understand any extreme environment where we can't look directly. And it really makes you wonder, doesn't it? What other invisible worlds could we now start to explore?